Okay. All right. Let's work. So your data, your grade data should be pushed to the grade book. We think that we're up to date. What's missing so far is quiz 11, the quiz that didn't exist. You won't see that. And exam 7 you have left to take, right? And MP7 you have left to take. But pretty much everything else should be there. I'm looking at Wade because he's going to correct me if I'm wrong about anything. Yeah. Okay, we don't have problems with the day extra credit up. Okay, you know if you've been doing it. So, let's see. I know you don't like that. I wanted to say one other thing. We have pretty much converged on the exam policy. We want to incentivize, we understand that it's going to be a game theoretic decision for you whether or not you take your absolute lowest score. And the way we want to do it is that I'm never going to get this right. Exam 7 can only be replaced by the maximum of your average and your lowest score. So we're going to actually remove the incentive or diminish the incentive for you to take an exam that you did, retake an exam that you did fine on earlier. We really want you to revisit material that was less clear to you before. Okay, so the formula as it is stands. It's the exam 7 is the max of your lowest score and the average of all your other scores. Yes? Did I get that right? Yes. So that de-incentivizes replacing exam 7 with any of your higher scores. Yeah? Yep. Yeah. No, it means, so we'll work this out later, okay? It means the formula as it is stands, okay? And as I communicated it to you before, and I can work through the numbers with you later if you want. I will also be sending out an email that clarifies it to make sure. I just didn't think about the case. I was always thinking of it as the lowest exam. It never occurred to me that, oh, you could get 100. Everybody who's ever gotten 100 can get an 100 on exam 7. All right. Okay, we need to talk, though, about graphs because we have a long way to go between where we are right now and where we need to be at the end of the semester. So, last time we talked about applications of graphs. And I assert that you've actually even implemented graphs before in this class. That, in fact, MP4, I think of MP4 as a graph MP. Now, every time you assert that something is a graph, your first responsibility is to communicate what the vertices are and what the edges are. So if I stand here and I say to you, MP4 was a graph MP, what were the vertices in the algorithm for MP4? What were the vertices? Yeah? Pixels, that's correct. And what were the edges in MP4? For the graph that we talked about in MP4? Yeah? Yeah, really good. So there was an edge between a pair of pixels if they are adjacent to one another in the graph. Hold on just a sec. Let me reconnect here. I don't know, I might not be able to do this. As such, our conversation in particular about implementing graphs is going to be a particular implementation, whereas most of your implementations of graphs are actually going to be custom to the application that you happen to be involved in. So for example, even though MP4 was a graph MP, there was no graph, right? You didn't have to pound include graph.h. There was no explicit graph. It's actually quite common for graphs to be implicit in the application. So let's see, typed there. All right, so let's move toward a deeper understanding of how we use graphs to implement, to solve problems. We're going to start with by making sure that we have a common vocabulary. Then we're going to spend some time on some classic implementations independent of your experience of MP4 and now MP7. We're going to talk in detail about traversal given those implementations. And then finally, we're going to open the can on graph-based algorithms. Now, we know we're going to end this semester on a total cliffhanger with respect to graph algorithms. It's supposed to tease you into running out of the room, running out of the semester, and signing up for CS374. So I don't know if they have room. Good luck with that. You might want to take your torches with you when you do that. Okay, so that's what our plan is, and we only have 6 lectures, including today, in which to get all of that done. So given that our time is short, the way I'm going to treat the vocabulary associated with graphs is to assume that you took your discrete math prerequisite, okay? The particular terms that I'm going to need from that discrete math prerequisite, CS173 or I think Math 213, whatever, are listed on this slide and the next slide. And by and large, I'm going to just refer to them as if you are kind of on the same page as I am. So I'm going to use these terms without definition a lot of times. But I'm warning you ahead of time what those phrases are. So you can go and refresh your memory if you'd like. So even if you have taken CS173, it might be a good idea to go back and review some things. The one thing I want to say about this set of definitions is I want to point out simple graph, the term simple graph. In this class, all of our graphs, if I forget to say it, all of our graphs will be simple graphs. And by that, I mean a graph that has no self-loops, so no reflexive edges where both endpoints are the same vertex, and no multi-edges. That is, there is at most one edge between a pair of vertices, okay? So if there is no, by default, our graphs are simple graphs. All right. I don't think I wanted to say anything else, but I have given you some example graphs. Actually, it's one graph. Oh, there's one more thing I want to say. I've given you an example graph here on which to reinforce your recollection of these terms. It's divided into these subgraphs, and sometimes in thinking about these terms, it's easier to look at a particular subgraph. Finally, the last thing on this slide that I want to point out is that every time I talk about a graph, I'm talking about the mathematical construct of a graph, and I mean a graph that is defined to be a set of vertices together with a set of edges, where those are sets in the mathematical sense. Now, a lot of times, we add a whole bunch of data onto this graph in addition to the vertices and edges, but a graph includes at least that stuff, a set of vertices and a set of edges. Now, furthermore, if I forget to specify it, I will always use n to denote the magnitude of the vertex set, and I will use m to denote the magnitude of the edge set. Okay? Any question about all that? All right. So Hi, welcome. Yay. I love when we have company. All right, so here's some more terms. Here's some more terms that I'm going to ask you to go look up instead of spending class time. What we're going to get to real quick, though, is some theory. So here's the deal. When we report running times of algorithms, we usually report those running times in terms of the number of vertices a graph has. Okay, that's just how we do it. And yet, many of the algorithms that we're going to deploy depend on the number of edges that the graph has. This observation is not very different from the observation that a lot of our algorithms on trees depend on the height, but we report those algorithms in terms of the amount of data. So just as we had to understand the relationship between the height of a tree and the amount of data it contains, in this context, we're going to understand the relationship between the number of edges in a graph and the number of vertices that it contains, okay? So that said, we're going to put both lower and upper bounds on the number of edges given the number of vertices. Okay, we're going to take n as our parameter of interest and express the number of edges in terms of that n. All right, so first, a lower bound, and first, I'm going to not demand that the graph be connected. Okay, so what is a lower bound? That is the smallest possible value on the number of edges given a graph of n vertices. The least possible number of edges in a graph with n vertices. What is it? You can say it out loud. 0 is correct. That's right. Oh, yay, that's right. Oh, yeah. We don't actually have to have any edges. The edge set is just a set. It can be the empty set, okay? So, in fact, that lower bound is 0 if we do not demand that the graph be connected. But, more interestingly, there's also a lower bound on the number of edges if we do demand that the graph is connected. Now remember, the definition of a connected graph is one for which there exists a path between any pair of vertices. So what is that least possible number of edges in a connected graph? N minus 1 is correct. Do you believe it? You might want to sketch a couple little graphs and see if you believe that it's true. N minus 1. Now that is a result that comes out of the air enough that we should probably prove it. If somebody walked up to you on the street with a result kind of like that, you might want to go, is that really always true? Maybe you should prove that that's true. In fact, there are approximately 37 different proofs of the fact that the lower bound on the number of edges in a connected graph is n minus 1. I'm going to choose one of them on the next slide. So we are actually going to do one of these proofs. Okay? All right. So now let's talk about upper bounds on the number of edges. First of all, I'm not going to demand that the graph is simple. That is, we'll allow multi-edges and self-loops, or self-loops. Not a simple graph. What's the upper bound on the number of edges? It's not a simple graph. So, yeah. And to the end, it's unbounded. No matter what you tell me the bound is, I can add another self-loop somewhere, right? Or add another edge somewhere and go higher than that bound. So, this is unbounded. One way of describing it is to say that bound doesn't exist. Or you can say that it's infinity if you like, if you view infinity as a number instead of a place. All right, so how many edges for a not simple graph? Infinitely many is one way of saying it. And the implication is The bound does not exist. Okay? All right. Now, though, probably the more interesting case, the more applicable case, the more useful case to us, is to argue what that bound is if we do constrain our graph to simple graphs. For argument, I'm going to draw us a graph. The one I draw has only 6 vertices, but I want to generalize the counting. So here's n vertices, okay? Imagine dots, okay? All right, so I want a number here. I want some expression for the number of edges in a graph of n vertices, the maximum number of edges in a graph of n vertices. Anybody got one they want to tell me? And choose 2? Where did that come from? Okay, so that's correct, but it requires some previous knowledge, right? It demands that you remember what combinations are, right? Which I think you do. So what does this mean? N choose 2. It's the number of ways of choosing 2 things, which in this case are the endpoints of an edge, from among n choices. Okay, very good. So that's a combinatorial argument for the value. Now, I think looking up the definition of n choose 2 would lead you to a different expression. What do you get when you expand that out? Anybody know? Yeah, tell me. No. Yeah? No. We'll get this together, okay? Here's how to get it. Here's how to get it. Imagine that we're going to draw all the edges in this graph, okay? Imagine that we draw this graph. We're going to draw all the edges. How many endpoints are incident on that edge? On that vertex. How many endpoints are adjacent to that or incident on that vertex? N minus 1 of them. Right, that's right. And how many of those are there? Well, there are n vertices. So what we have are n times n minus 1 endpoints. Every edge has 2 endpoints. So the total number of edges is endpoints divided by 2, right? Endpoints divided by 2. So this formula is n factorial over n minus 2 factorial 2 factorial. So that cancels a whole bunch of, the guy on the bottom cancels. And you end up with this. Okay? Does that make sense? Okay. All right. Any question about that? So notice that there are 2 totally different ways of looking at the same problem. One was a combinatorial perspective. Another one was kind of this geometric perspective, right? Where we took advantage of the fact that each one of these are going to behave in the same way. There's one more way of looking at this, and it comes from the fact that I actually think this is a familiar expression to you. And in particular, if I write the beginning of that expression, what does the rest of it look like? You always need one of these, k equal, okay, we can start at 0 if you like, up to n, and, except that it's really n minus 1, but okay, of k. Right? You already know this. You already know that this is represented by this sum. But why does that work? Well, let's draw the graph again. Let's draw all the edges in the graph again. I'm going to start here and draw all the edges. How many did I draw? I know I drew 5. Pretend the graph has n vertices. How many did I draw? N minus 1, that's right, n minus 1. Now I'm going to add the vertices, or the edges that come from this vertex. How many of them are there now? N minus 2 of them. So now I've got n minus 1 plus n minus 2. How many of them are there, here to be drawn? N minus 3, okay, dot, 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 all the way down to here, to this one, where there's one edge to draw, and what's left to be drawn for this one? None. There are no more edges to draw. So in fact, it works out that this sum is the same. This sum represents the solution to the same problem. Now, the reason I do this, the reason we spent 5 minutes on this instead of 30 seconds is the following. A lot of times when you're solving problems about algorithms in particular, there are many, many different ways of looking at the problem. Sometimes it's combinatorial. Sometimes you're going to be able to see a problem as a counting problem. Sometimes it's a geometric problem where you just you draw some things and you go, okay, there's endpoints, there's edges, and you just draw it and you see the expression as a geometric expression. Sometimes there's an algorithm that helps you build up a solution to a problem, and you see it incrementally. And I'll tell you that when you're trying to solve the problems in an algorithms course or in life, you're going to need a lot of different approaches to the same problem. In fact, a lot of times homeworks will say, look at this in 374, we'll say, okay, you can solve this iteratively, but how do you view it combinatorially? Explain your solution combinatorially. And having these different ways of looking at a problem are very, very helpful. Now, why do we do this here? Because I want you to see it in a very simple, safe environment before you're actually asked to do it in a difficult. This is like the first example of an explanation that has lots of different perspectives. All right, any questions about that? Okay, there's one more little thing. There's one more little thing that's going to come up later that I want you to give me the answer for, because I'm tired of talking. So I need you to give me the answer for this. Here's this expression. We're going to add up over all the vertices in the vertex set their degree. So we're going to sum the degrees of all the vertices. What should I write here? No matter what, when you add up all the number of vertices, when you add up all the degrees of all the vertices, what do you get? 2m. That's right. We are going to need that later on. So that is right. Again, just to reinforce, it's because when you add up all of the degrees of all the vertices, you're counting endpoints. And we already said that overcounts the edges by a factor of 2. Okay? Any question about anything on this page? All right, so I want to prove the one thing that is left there as kind of a mystery, and that is the following theorem. Every minimally connected graph has b minus 1 edges, where I said the word b, but I meant the cardinality of the vertex set, okay? Now, I changed the wording a little bit. Minimally connected simply means if you remove an edge, it's no longer connected. The implication of something being minimally connected is that it's acyclic, and it's connected, right? Because that's what we said. So this is really an argument about the number of edges in a tree, because it's connected and acyclic. So another way of thinking about this is as a tree, or a tree. Okay? All right, So the way we're going to do this proof is to consider an arbitrary, minimally connected graph, and I've given it a label there. Most of this discussion is about labeling the graph, I'll tell you. There is one small, lemma that we're going to need here, and it's so that we can apply an inductive hypothesis. It's kind of a technical detail, but it would be a 1 point off of our proof if we didn't include it, okay? The lemma is that a connected subgraph, that is, any connected subgraph of a minimally connected graph is also minimally connected. Okay? It doesn't somehow become more robust just by becoming a subgraph. It's also minimally connected. All right, and that's it. You'll tell me when we need to apply that. Okay, and then I've stated the inductive hypothesis there, and you can tell me when we need that as well. So how does our proof go? We've got this arbitrary one, this arbitrary minimally connected graph. Now, either the cardinality of the vertex set is 1 or it's not. Let's take the case that the cardinality of the vertex set is 1 first. Cardinality of the vertex set is 1. There it is. That's the vertex. How many edges does that graph have to have? Yeah. 0, duh. Right? Remember, these graphs are by default simple. So you can't have self-loops. And if you try to put an edge on a single vertex graph, there's no place for that other edge to go, right? So you can have no edges here. And indeed, if you look, a minimally connected graph of one vertex has no edges. And look, here you've got the size of the vertex set, which is 0 minus 1 equals 0. Check. Okay? Thesis holds. The theorem holds. All right, but things are about to get much, much, much more interesting. Suppose we have a graph that is bigger than that. The vertex set is bigger than 1. Now, I've drawn one here just for illustration, okay? It's intended to be an arbitrary one. You can pretend that, several years ago now, I created a random graph, and there it was, okay? Now, here's what we're going to do. I want to choose any vertex. Any vertex. Somebody want to volunteer a vertex? Yeah, what vertex would you like me to choose? V. Okay. I can choose V. It'll be more interesting if I choose W. Okay. Students always choose W, except Mark, of course, because he's an innovator. Yeah. No, he's an innovator. He's going to change the world. And so I'm going to do W. It's a way, yeah, never mind. There are 2 V's? No, they're not. Oh, yeah. You're right. I'm going to take, yeah. There you go. So I'm going to choose an arbitrary vertex, and I'm choosing W in this case because I do think it illustrates what's going on a little better. Okay, but in general, it will work for the choice of V as well. And here's what I'm going to do. I'm going to let it be its own component in the graph, and I'm going to call that component 0. And then first I'm going to remove all of its incident edges. Okay, 1, 2, 3 here. And I'm going to let D denote how many of them there are. So the degree of the vertex that we removed, which in this case was W, is D in general. Yes, I can see it's 3, but in general it's going to be D. Now, removing those edges breaks the graph. And it breaks it into the component that holds the vertex that we just selected, and I'm going to call that component 0. And how many other components? How many other components are there? D of them. That's right. There are D of them. Okay? So let's label those for just a second. Let's take a breath and get a label on all of those components. All right. So it breaks it into D plus 1 components. C0 has, as its vertex set, the one that we removed, and it has no edges. Okay, a set of vertices looks like this. And in general, see, the last one looks like VD and ED. Okay, and C1 looks like B1, E1. Okay, it's only C0 that we know anything about at all. The rest of them are just, I don't know. So, for example, still, here's C1, C2, you know, etc., all the way up to the last one. Okay? All right. So, we've got everything labeled. Now we can do some arguing about it. In fact, we can figure out, based on all the labeling that we have, that the size of the edge set for each of the components is, what would you write here? How big are the edge sets for each of the components? I wish I had big hands. I could cover up everything that I would need to, right? Look at each component. It's just a little graph. It's just a little graph with V sub k vertices and E sub k edges. How big is E sub k? You want to tell me? Yes, you. No, yeah, you can look around, but no, you. Do you want to tell me? Guess. Close. Oh, there's a -1 there. Very good. And the K goes here. V, good. And I need some magnitude symbols, right? So this is the application of the inductive hypothesis. The inductive hypothesis tells me about something about the edge set. It tells me how many edges are in a minimally connected graph, right? A smaller one than the one we're arguing about. So this is simply stating that, look, all these small components, they're just graphs. They're just subgraphs that are minimally connected. By the inductive hypothesis, we know they have the number of vertices -1 edges. Okay, so this is all we need. Now all we have to do is add up the total number of edges. So the first thing is those D edges, so that the magnitude of the original edge set is the D that we removed plus the sum for all the other components, 1 to D, of the magnitude of the edge set, which we know is, from inductive hypothesis, we know that that's just the vertex set -1, which is just D plus the sum from k equals 1 to D of VK minus D. Oh, look, I love when things cancel. What's this? We're adding up all the vertices in all the components except the 0th one. So what is this? Look, it's all the vertices except that one that we chose at the start, right? Yeah. So this sum is the whole vertex set -1, which was what we wanted to prove. Yay! Okay. Any question about that? Okay, so here's what I want you to do. I want you to reflect on your internalization of this proof process, okay? And I want you to sort of imagine that I hide the screen and I give you a blank version of it in front of you. And I want you to self-assess how you would do in reproducing it, okay? And tell me on a scale of 1 to 4, I'm not going to give you a middle value here, on a scale of 1 to 4, how you would do, where 4 is I would rock it, okay? And 1 is okay, which is fine, which is fine. So raise your hand with your reflection on how you're feeling about the proof itself. Could you reproduce it? Or no way, Jose? Okay, raising your hand is fine. Okay, so I'm seeing, I think, an average of 2 here, just FYI. Okay, all right. Can I talk to somebody who's like feeling iffy about it? Where would it get hard? Where's the difficulty? What was unclear? This is true confessions moment. What do you think? Yeah? You want to tell me? Uh-huh. Yep. 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 So they're all, so how do we split up the rest of them is the question. So where is the rest of them? Where is the rest of them? When you say them, every vertex lives in one of those components, right? So the rest of them is all those components. We take the whole graph, we pull out one vertex, and it falls apart. We let it fall apart. It's going to fall apart into D components, all of which are connected. Does that make sense? No, you don't have to do it recursively. You don't have to do it recursively. You do it once, and the inductive hypothesis gets you the rest of it. Right? It counts for you what those components look like. That's it. That's the magic moment where you go, oh man, I can't think about this at the next level. You let the inductive hypothesis handle it for you. Yeah? Uh-huh. Yeah, yes, yeah. So that is also the basis of a different proof. There are nearly 40 proofs for this. The one thing that makes that a difficult proof is that you have to argue that every graph can be constructed in that way. So that's the difference here. I start with an arbitrary graph. I make no assumptions about my graph. So you're adding to it, and you have to be able to argue that that added graph is an arbitrary one. Does that make sense? Okay, yes, there are lots of proofs of this. There are lots of proofs of it. Okay, so I'm going to keep going if that's okay. The next page contains implementation, okay? So as I said before, there are lots of, that most of the implementation that you do for graphs they are sort of custom in the context of a problem that you're solving. But we're going to look at particular implementations, and the abstract data type that we use to talk about those particular implementations, it can be as complex as the application of the graph that you're doing. So, but what must be true is you have to be able to build a graph and change a graph. And so the piece of the abstract data type that I'm giving you here is really a constrained view on what you might include. We need to be able to insert vertices and edges. That's how we build them up. It's reasonable to imagine that we should kind of look at how hard it is to remove edges and vertices or change our graph. It turns out to be very useful in lots of different algorithms, that when I give a vertex, I need a function that will return, that given a vertex, I need a function that will return the set of incident edges on that vertex. Okay, so this returns set of incident edges. Similar, it's also quite useful in algorithms to be able to take two vertices and tell me immediately whether they are adjacent in the graph, which is equivalent to asking, is edge V1, V2 in the graph? But then, as a way of reminding you that, yes, these are just a smattering, I want to talk a little bit about some functions that might exist if this were a particular kind of graph. Oh, and most graphs are particular kinds of graphs. So this is one example of a particular kind of graph that we're going to be interested in, and that is for directed graphs. So I'm imagining that edge E is specified as E equal a pair of vertices. In this case, it's an ordered pair, and by convention, we decide that the first vertex in the ordered pair is the origin. So the origin of E returns U, and the destination of that same edge E returns V. Okay, so it's just vocabulary associated with directed edges, okay? But they are something that you would have to implement. We are going to spend all of our time talking about undirected graphs, but it's probably a good idea to sort of think, how would I implement this if it were a directed graph? And that might actually come up in some conversations. Okay, so let's go toward implementation. Every implementation that you will do of graphs will have some kind of structure. Every explicit implementation you will do of graphs will have some structure to keep track of the vertices, another structure to keep track of the edges, and then another structure, possibly associated with one of those, that reflects the connectivity of the graph in some way. There are three classic implementations that we are going to talk about, starting with what's called an edge list. Now, here's how this implementation goes. It has a structure for the vertices, it has a structure for the edges, and the additional structure that keeps track of the connectivity of the graph is actually missing. So all we have is the vertex structure and the edge structure. Now let me talk about that vertex structure for just a minute. And the same applies to the edge structure too, but I'll talk about it in the context of the vertex structure. So here's the thing. We're assuming that every vertex has some unique identifier. Now, if that unique identifier is a vertex, then your key is going to be the vertex, and probably you're going to use an associative array or a table to keep track of the location of the vertices, okay, or the data associated with the vertices. If, on the other hand, you decide that your vertices will be characterized by some small integer, which is a perfectly reasonable thing to do, then this vertex table will just be a small array, right? Like where you have vertex 0, vertex 1, vertex 2, etc. And that's perfectly fine too. No problem with that. I won't do that here. I'll kind of be viewing the vertex structure as a table or an associative array, but this could just as easily have been an array. All right, so all of that said, for edges, we also have identifiers, that is the kind of the name of the edge. We're going to have a table, just like we do for edges, for vertices, and into this table we're going to store the adjacent vertices. So we're going to store the endpoints, the vertices at each endpoint of each edge. So that graph right there is stored in memory like this. UV, VW, UW, and ZW. Are there any questions about that? I think I might have a question if I were you. I think something that I wrote might have surprised you. Yeah? Yeah, the order doesn't matter. This is an undirected graph, which means if I'm looking, imagine that I'm looking for edge UV, I have to also admit the possibility of VU. So I have to consider those in my evaluation, my equality, as the same thing. Okay? All right. I chose a set of functions that get at all the important issues that arise in evaluating a structure. So we're going to be comparing these functions across our different implementations. So we should start by assuming these are the functions that we're comparing and assessing the runtime for them. Okay? So how long does it take to add a vertex to this structure? There, I did it. How long should that take? That better take constant time. We better be using a structure for our vertex set that admits constant time addition. Okay, so I'm going to say that's big O of 1. Okay? Now let's remove a vertex. There, I did it. That's constant time too, right? What's wrong? What? What problem do you have? What's your problem? What's the problem here? Yeah, look. We've left edges dangling. That's not a graph anymore. When we say remove a vertex, we usually mean remove the vertex together with its incident edges. Okay, so what we really mean is remove V and remove the incident edges. So how long does that take? My only alternative, I only have V, right? I'm parameterizing the removal by the name of the vertex. I only have V. So the best I can do to go looking for those incident edges is to query the edge structure iteratively. Hey, do you have a V as your endpoint? Oh, you do. You're out. Hey, do you have a V as your endpoint? Oh, you do. You're out, etc., etc. Okay? So what's the running time of that? Big O of M. Good? Good. Any question about that? All right, let's do the next one. Now I have two vertices, and I just want to check to see whether they are adjacent in the graph. That is, whether or not there's an edge between them. What's the algorithm for doing that? What did you say? Check the edge list. How do we do that? Iteratively, again. Our only alternative is to traverse the edge list. All right, finally, I want to return the set of incident edges. That is, in this case, I'm going to want to return AB in the example. What's my algorithm for doing that? Yeah? Yeah, same algorithm as removal, except you don't remove those edges. You have to go looking for them. You don't know where they are. So again, the running time is big O of M. Now, what I think is that all of you are thinking, well, shouldn't you just, right? Shouldn't you just what? Keep track of the edges incident on a vertex? Yes, that's what you should do. That's what one of the auxiliary structures we're going to talk about next time does for you. Okay. Bye. Have a good weekend.